Hi everyone, I am Vanita. I am doing BE in Electronics and Communication Engineering in SVCE Bangalore. I am from Honda section. Today my subject is physics and the topic is dielectric applications in capacitors. Introduction. A capacitor is a device which stores electric charge. Capacitors vary in shape and size, but the basic configuration is two conductors carrying equal but opposite charges, as shown in figure 5.1. Capacitors have many important applications in electronics. Some examples include storing electric potential energy, delaying voltage changes when coupled with resistors, filtering out unwanted frequency signals, forming resonance circuits and making frequency dependent and independent voltage dividers when combined with resistors. In the uncharged state, the charge on either one of the conductors in the capacitor is zero. During the charging process, a charge Q is moved from one conductor to the other one, giving one conductor a charge Q plus and the other one a charge. A potential on the capacitor as a whole is zero. Q difference is created with the positively charged conductor at a higher potential than V delta, the negatively charged conductor. Note that whether charged or uncharged, the net charge, the simplest example of a capacitor, consists of two conducting plates of area which are parallel to each other and separated by a distance d, as shown in figure 5.1. In many capacitors, there is an insulating material such as paper or plastic between the plates. Such material, called a dielectric, can be used to maintain a physical separation of the plates. Since dielectric breaks down less readily than air, charge leakage can be minimized, especially when high voltage is applied. Experimentally, it was found that capacitance C increases when the space between the conductors is filled with the dielectrics. To see how this happens, suppose a capacitor has a capacitance when there is no material between the plates. When a dielectric material is C0 inserted to completely fill the space between the plates, the capacitance increases to C is equals to Ke C0, where Ke is called the dielectric constant. In the table below, we show some dielectric materials with their dielectric constants. Experiments indicates that all dielectric materials. Note that every dielectric material has a characteristic dielectric strength 1K is greater than E, which is the maximum value of electric field before breakdown occurs and charges below to flow. The fact that capacitance increases in the presence of a dielectric can be explained from a molecular point of view. We shall show that K is a measure of the dielectric response to an external electric field. There are two types of dielectric. The first is polar dielectrics, which are dielectrics that have permanent electric dipole moments. An example of this type of dielectric is water. Properties of dielectric materials. Following are exhibits the dielectric materials. The energy gap in the dielectric materials is very large. The temperature coefficient of resistance is negative and the insulation resistance is high. The dielectric materials have high resistivity. The attraction between the electrons and the parent nucleus is very strong. The electrical conductivity of these materials is very low as there are no free electrons to carry current. Let us see about the applications of dielectrics in capacitors. A major use of dielectrics is in fabricating capacitors. These have many uses, including storage of energy in the electric field between the plates, filtering out noise from signals as part of a resonance circuit, and supplying a burst of power to another components. The larger the dielectric constant, the more charge the capacitor can store in a given field. Therefore, ceramics with non-centrosymmetric structures such as the titanates of group 2 metals are commonly used. In practice, the material in a capacitor is in fact often a mixture of several such ceramics. It is generally desirable for the capacitance to be relatively independent of temperature. Therefore, modern capacitors combine several materials with different temperature dependence, resulting in a capacitance that shows only small, approximately linear temperature related variations. Thank you for watching.